So if you remember last time we were talking about replicated log, we talked about basically primary, backup, replication. Then we talked about replicated logs, and that was where we finished the last time talk, if you remember. So today, we talk about how we can replicate the logs, and the log is basically having the truth of the system or the latest basically condition in the system. So today we're going to talk about the consensus module that you can see here, and we want to make sure or talk about how basically different machines can get can be agreed on a same value. Okay, so that's the whole group. 6 people are here.
Yes, Professor.
Okay, you ready to talk about it?
Yeah, of course.
So I just okay, perfect. So I just wanted to remind you where we're standing. Okay, so they're going to talk about the consensus now. But what I'm trying to say is, like, remember what we discussed last time. So now we're going to talk about the consensus, how we're achieving that using Paxos and then using the raft. Both are the basically consensus algorithms. So later, if there was something missing, maybe I will talk, but I saw that the presentation is quite covering everything. So I'm going to stop sharing. You can start sharing your screen.
Okay. Antonio, you talk like there it is. There it is.
Yeah, can you see it?
Yes. Yes.
Juan, if you want to begin.
Yeah.
Okay.
I think we are all ready.
I will start now. Hello, everyone. The topic for today is Paxos Made Simple. It's actually a paper, a work done by Leslie Lamport. So can you please do the first slide, Antonio? Well, basically, Paxos algorithm is another tool used to make a fault-tolerant distributed system. It's one of the most simplest and obvious of the distributed systems algorithms. What Paxos do is a consensus, is an algorithm that make consensus between agents. These can be servers, computers, or several individuals connected to each other in a distributed system. Leslie Lamport came up with Paxos in the 80s. Actually, he did a good and a great job doing it. But the thing is that at that moment, it was something similar made by Lynch and another researcher called Liskov. They actually built a successful distributed system using this kind of algorithm. But the thing is that there was not a mathematical proof about it. And Leslie Lamport, what he did was, okay, there's no mathematical proof. So what I'm going to do is to show that there was no evidence at all that this is done correctly. He just saw the work of Lynch and Liskov. As I said, no mathematical proof about Paxos. And he wanted to formalize the system and provide the evidence. It was not correct. And he done the opposite. It was a complete breakthrough. But the problem is that Lamport came up with a history of a pretty weird and complicated history about Iceland called Paxos and some Greek parliamentarians working there. Just nobody get it. And he wanted that work to be published, but since nobody get it, nobody wanted to publish it. So he just saved the work. And then after some years, somebody told him, okay, let's going to publish it. And then he had to make this work more simple, and that is why. And that is when it came up with Paxos Made Simple. That is actually the paper that we used in order to do this presentation. And that's it. And next. Well, the problem that Paxos needs to solve is that there is a lot of agents there. They need actually to choose an option. That is why we can call them as a collection of processes that can propose values. With processes, I mean the agents. Proposed value must be chosen. If no value is proposed, then no value should be chosen. In order to make this explanation simple, for now, we are going just to use two options, option A or option B. The value that actually is proposed by one of the agents is the one that normally is, or generally is the highest one. There is some safety requirements. Only one value that has been proposed may be chosen. So means that when one value is sent to other agents is the one that must be chosen, no other ones. Later, we're going to see like a table where this is better explained. Only a single value is chosen, and an agent never learn a value unless actually have been, this is kind of complicated because not all the agents are aware that their decision is being chosen or it's actually being done, but we will work on it further. All the agents in the group can have three roles, can be proposers, can be acceptors, or can be learners. The goal is to ensure that some proposed value is eventually chosen. And if a value has been chosen, then an agent can eventually learn the value. The proposers are the ones who propose the value to be chosen. This is simple if something is not happening. One or several agents propose a value. And also this proposal is in one of the phases that Paxos is split because are two phases. The acceptors are the ones that accept the value. These agents review all the values and take the bigger one, as I previously said, in order to choose one option. And the learners learn the value accepted. The learners can be other agents that are actually part of the group, but they are not like participating. They just receive the information. You know what? We chose this one, and you have to learn it. And they say, "Oh, okay, we will learn it, and we will make a decision." In an implementation, a single agent can take any role, and the mapping or the nodes do not concern us here. What I mean with the mapping is, is the configuration of the system, how they are ordered, like in the previous topics that we saw before. There's like special arrangement and that kind of stuff. Here, it just do not matter. Next slide, please. Oh, hold on. Okay, so let's assume that agents can communicate each other by sending messages. The agents can work in arbitrary speed, may fail by stopping, and may restart. In order to make this, the Paxos algorithm, well, actually, what I want to say with this is, in the whole group, maybe one of them just stop work, and the other ones can keep working without any problems. Basically, this is what it is. The messages cannot be corrupted, which is something very, very good. When they are passing information, everything can be fine. Okay, so next. Oh, and also I forgot, for this kind of environment, we will use regular asynchronous models like the ones that we used before. Or I mean, we already learned before asynchronous, that they do not have a, like the Leslie Lamport, when we saw clocks and everything. I mean that. Okay. And well, the objective is make a consensus between a group of agents. They must choose between the two options, and there's no way to split them up. All the group, once they chose a value, all go there. There is some constraints on this. There is no predominant decision taker agent. I mean, there is no leader. All of them can assume this role. They just start, one of them just start all the configuration, and they send a value, and all of them, we're going to follow it in case if it is the biggest one. Agents do not split, must be in option A or B. The decision must be taken fast. This is very important because in a real distributed system, for example, in a store, when the customer needs to buy something, obviously this has to be really, really quick. Agent-to-agent communication, the value is going to be sent to each agent, and that is the way it works. Next slide, please. Okay, hold on. Well, in a real system, we need multi-paxes. This means that we have to run paxos over and over and over and over again in order to make a complex system. In the second slide, we saw that we just had option A or option B. In a real world, this just cannot be, is unrealistic. So we have, so in a real system is running one over and over and over and over. In this way, the group can achieve consensus. There is no clear guidance about the decision, not splitting. Okay. As we can see here in this square, there is 4 servers. All of them are working in the distributed system. One of them can fail. It doesn't matter because all the rest of them can remember that information. If this happens, we can say that all the computers are equivalent. Failure is not a problem, and the system can keep communicating with each other, and the others can continue with the work. When we are running paxos over and over and again, we can make a lot of decisions. So if you see the small square, you can see log in the upper part, and all the servers already chose one option. Maybe server 1 chose option A for the first day, option 2 for the second day, server 3 option B for the third day, and server 4 again choose B for the fourth day. So that is why that is how we use multipaxes to build an option log that can help us to run a system in the real world. It's basically the main idea. So next slide, please. This is what I was talking about Paxos working on their two phases, phase one, phase two. In the phase one, a proposer, well, he's a value. A proposer selects a value and sends, send it and prepare the request with a number for a majority of acceptors. What I mean with this, what I mean is, for example, the group is just there, and so suddenly one of the servers sent a value. Okay, here it goes. In the phase two, the proposer receives a response. I'm sorry. This is another part. Once the agent that received the response is going to send it back again to the proposers that actually sent it, and he's going to, and this is when phase two came in, and they're just going to communicate, and there is like it's coming in the next slides, but actually the proposer say, here it goes. Do you want it? Oh yes, no. Here it go again. So this means that it's accepted. Okay, well, yes, we accept it, and there is another response back to the learners. Can you please go to the other one? This is more clear. This is actually more clear. We have, in this example, 3 servers, 1, 2, 3. The first one is a proposer and also is an acceptor, and the other ones are acceptors. Just hold on. I have my notes here. Okay. In it, the proposer needs to create a round identifier. Needs to have 2 properties. Must be the biggest one in order to be accepted. And yeah, but and we generated with this I++ code. Okay, so basically the 42.1 is sent to the other agents, the other 2 acceptors. They are going to prepare it. They're going to evaluate this number. If it is bigger than the other one, then it's going to write down this number in a function called promise. Otherwise, for example, if there is another bigger number, it's not going to work, and it's going to be not acknowledged, or as you already, or how you prepare the program to respond. Next slide, please. Okay. Once the acceptors receive the number and already evaluated, they're going to send back this promise function to the proposer. That is going to review it, and it's going to say, oh, okay, seems it was accepted. So I'm going to move on with the next step. Next slide, please. Okay. Once the proposer saw the function, the promise function is going to send back an accept function with the same number, but also with the value or the option that actually is marked under this 42.1. And again, the acceptor is going to say, okay, 42.1 is going to be equal to the same, is the same still? If it is the same, they're going to write accepted, and with the value that was chosen. Next slide, please. Okay. Now, all the agents already accepted the value. They saw that the 42.1 with the A value is the biggest, so all of them are accepted the value. If there were some learners, like I said before, they're going to learn this value. They're going to say, oh, look, we done this quotation, if you want to call it this way, and we chose this value. So join us, and we are going to choose option A. And this is, if you see in the down part of the slide, I already placed the phases where actually Paxos is doing it. The prepare and the promise option is the phase 1. And basically the phase 2 is the acceptation phase. So this is how Paxos algorithm work in a simple way with 3 servers that actually are the minimum that a Paxos algorithm can accept. And success is done. We chose option B. We're going to pick A. Yeah. And Antonio, I think it's your turn.
Yeah. Okay, so that was the main algorithm that Paxos works with. Further on, we're going to check where can failures happen and how Paxos mitigates these failures. So here we have, again, the whole chain, the whole algorithm. And we can have the first failure in the acceptor phase. Say S1 is trying to prepare the other servers to accept some kind of message. However, let's suppose that S3 fails or didn't receive the message or whatever, and he doesn't receive the prepare phase. So only S2 replies. Only S2 sends a promise, and S1 also acts as an acceptor here. So he's also, like, he promised himself, we could say that. So in this case, we have the majority. The majority accepted the majority is prepared to accept a message. So in this case, well, Paxos relies a lot in majorities. It is a very crucial thing of Paxos. So in this case, it doesn't matter if S3 didn't say anything. Still, we have the majority is prepared. The majority promised. So S1, as the proposer, is going to send the message of accept. He's going to send again his ID. The ID of S1 is 42.1. And he's going to send the accept messages to all of the nodes. Doesn't matter if S3 is still down, it's going to send it to all the nodes. And well, consensus was reached before. It was reached at the promise phase. So all of the nodes should accept the message in the end. Another phase where it can fail is the proposing phase. Say we have the proposer, but the proposer failed. So nobody is sending any kind of message. There's the line is dead. So in this case, what Paxos does is that just another server takes the job of being a proposer. So in this case, it could be S2. S2 could take the new role of being a proposer and then accept it. So that is how we mitigate this failure. Going on, another part where the proposer can fail is when the proposing phase, here we have the prepare. The prepare phase was done correctly. Then the other servers promised, and everything's going fine until then. However, the proposer then just dies. Something happened with the server, and it doesn't send any kind of accept message. So S2 and S3 are waiting, are waiting, are waiting. Time is going on, and well, in this case, it has like a timeout, and then S2 in this scenario is going to take the role of being a new proposer. He just wants to take a decision. So in this case, he ignores the previous promise, and he's going to be the new acceptor. So he sends a new prepare request, and S3 replies. He says, since S2 has a higher value than S1, S3 should accept the proposal of S2. So S3 is going to promise to S2 that he's going to accept a new message. So S2 receives, he has the majority, he has his own promise, S2, and he has the promise of S3. So he's going to send the accept message. In this case, we're also accepting the item A, and he's going to send it through all of the channels. Later on, S1 will recover eventually, and he's going to receive that message that that A was the item that was accepted. Then we have the accept. We can fail in the accepting phase. We can have S1 doing the whole algorithm just fine. Then we're going through the accept phase. However, only one of the messages went through the channel. Then S1 failed. So in this case, S2 isn't aware that item A was accepted. So we are here in kind of the previous situation of the previous slide, where S2 is still waiting and waiting for an accept message. In this case, S2 is going to take the lead. He's going to promote himself as a proposer, and he's going to send a prepare message. So S3 receives the prepare message, and since S3 has a higher value than S1, he has to promise it. However, in this promise, S3 is aware that a consensus has been reached before. So an item has been elected before. So he's going to tell S2 that, well, he promises to listen to him. However, he's going also to piggyback the value that was chosen before, in this case, the item A. So S2 receives that promise with the value, and he's going to just accept that reality that consensus was reached before. So he's going to send another accept message through all of the nodes with the item that was selected before. So all of the nodes received the message that A was accepted. And finally, another type of failure that we can have is that we have two proposers. Well, we have multiple proposers, which is common in a multi-paxos system. In this case, S1 is telling, well, in this case, you can notice in the slides that the ID changed. The ID now is timestamped. So that the ID is chosen, it's programmed by the programmer. So in this case, the programmer chose to use timestamps as an ID. So in this case, S1 is going to send a prepare message with his own timestamp, and he's going to receive promises from other acceptors. However, S2 was waiting, and didn't receive any message. So it's going to send a new prepare message with a new timestamp, which is higher than the previous timestamp. So S3 is going to accept it because it has a higher timestamp. So he's going to promise to S2 that he's going to listen to him. Later on, well, S1 was like a little slow, and he took his time, and he then later on sends his own accept message. However, S3 just promised to S2 that he's going to listen to him, so he rejects the accept message. So in this case, it is a matter of delays. So S1 and S2 are sending a lot of proposals very quickly, and the solution to this problem is really simple. It's just to set an exponential backup. Say every time S1 gets rejected, he's going to wait more. He's going to, if he gets rejected quite a lot, he's going to wait even more time every event. He's going to wait and wait more, so that another proposers or he himself can get all like in a good time, so that messages can be received like in sections. Okay, so now we're going to see a little example of how Paxos works in a real scenario. Say we have here Roberto. Roberto is a client. He has a bank account. This bank account is replicated. There are 3 replicas with the same account balance. And here notice that we have a log. So in the first log, we have the current bank, the current amount of money in the bank. So then we have, well, say we want to add $100. These $100 have to be replicated through all of the nodes. So all of the nodes have to be aware that $100 were added. And this creates a new log. Now we are in the log 1 position. And now we're going to just explain step by step how operations are made. In this case, Roberto wants to withdraw $30, and Roberto is a client, and he is asking the node 1 to make that request. So in this case, node 1 chooses himself as a proposer. He is going to send a message. He's going to tell all of the other nodes in the system. He's going to tell them, hey, prepare. We're going to write on log 2, and we're going to subtract $30. So all of the nodes hear him. All of the nodes promise to write on log 2 and to also withdraw, well, the value of minus $30. So the proposer receives all of the promises, or at least the majority of them. And in this case, node 1 sends the accept message to all of the nodes. He tells them to accept that we're going to subtract $30 on log 2. And well, check here the replicas. The first replica already has the new account balance, which is the correct one, and replica 3 also has the correct amount. However, node 2 couldn't receive this message. So in this case, there are two possible, well, what's going to happen with node 2? In this case, we have two possible solutions. Node 2 will receive an accepted message with log position 2 and the value of the operation. This would mean that consensus was reached before, and the node will catch up later on with the rest of the nodes. Or node 2 could try to propose a value on log 2. However, we saw this previously. This case is this one that he's going to try to prepare the other nodes to listen to a new value. However, the other nodes are going to tell him that consensus was reached before, and they're going to piggyback the value. So in that case, all of the nodes reach a consensus, and all of the nodes have the most recent value, which is the correct one. So talking a bit about performance, the paper doesn't talk about this. However, we did a bit of research. When we are using single taxes, which is what Juan and I have been talking through all of this presentation, we have to do two network round trips. That is when we are asking or receiving messages from other nodes, and the nodes have to perform two disk writes, which is they have to remember what they are promising, and they have to remember what was accepted. However, when we use multipaxes, which is something that also wasn't very that wasn't mentioned in the paper, but in multipaxes there is some kind of optimization that only one network round trip has to be done, and only one disk write has to be done, and it works just fine. So talking a bit about the localization of nodes, it is clear that if we have all of the nodes in the same building, latency is not going to be an issue. I mean, the network should be pretty fast, and consensus should be reached pretty fast as well. However, this decreases the reliability of the system, because the electrical system of the building may fail and all of the servers go down. So we could expand the location of the nodes, we could distribute them along a country or whatever, and in this case we increase the latency and we increase also reliability. So the system is going to be a bit slower, but we have like increased the level of safety. However, let's say we have a storm or a tsunami just and just devastated the country, or I don't know. So the system fails as well. So in this case, we can send the servers we can distribute them even more to other countries, and this also increases latency, but it also increases reliability. One way to tackle down latency, not completely, but to mitigate it a bit, is to bundle up the transactions. So we send a lot of we send more messages per every trip, every network trip. So this helps a bit with the latency. And also, in this case, Paxos, as I said before, has to relies a lot of in the majority of the system. So majority has to be working on correctly, so consensus can be reached. So say we have m number of failures, and Paxos can do just fine if we have a 2 times m plus 1 number of nodes. So this is that we have, in simple terms is just that we have to we need to have the majority of the system up and running. So just key takeaways. I mean, Paxos is a little complicated, but but here's like some kind of well, just the key takeaways is that reaching consensus is crucial in distributed systems, so operations can happen between the nodes. Paxos is a fail-stop oriented approach, in the meaning that some servers can fail or some servers can restart. There's another type of systems that are called Byzantine fault tolerant, which this only means that well, a system that is Byzantine fault tolerant is one that can detect a hacker. Let's say a hacker is trying to mess up with the system, and a Byzantine fault tolerant is designed to mitigate this kind of problems. Also, a Byzantine fault tolerant system helps with corrupted data, but Paxos is not meant for this. Also, well, well, as I talked before, Paxos tolerates failures in all of the stages of the algorithm. It heavily depends on the acceptance of the majority in a system, and it can handle m number of failures in a cluster with 2 times m plus 1 nodes. And well, that's it. We relied a lot in these 2 videos because the paper is a bit complicated to understand. But if you want to check more the information, you can check YouTube, which I recommend. And that's it for us.
Thank you guys for the talk. It's open for a question and answer.
Okay, I have a question.
Yes.
What is the purpose of learners? Because we see in the examples, we don't never talk about learners.
Oh yeah, learners happen like in the background when, let me just see. When
Well,
the when the accepted message is traveling the system, there are some learners that just write what's being accepted. So they act like they just keep the log of the items that have been accepted before.
yeah, actually,
So-
it's when there is a round from a proposer just pick a value and it's attached or append that option to that value, then send it. Not all the agents in the group are acceptors or proposers. The rest of them are learners. Let's suppose that you have, I don't know, maybe 100, 200 agents in one distributed system, and a proposer just sent that proposal to, I don't know, maybe to 20% of it, but maybe there is another proposer in another, let's say 40% of the group sending another proposal. That is why we explained that is when the phases came in. You know what I mean? So in the second phase, that is actually what is going to happen. They're going to evaluate if the proposal of the proposer is the biggest one, and they're going to compare, and the remaining ones are just going to learn the value that was accepted between maybe 2 proposals. You know what I mean? It's clear.
Well,
you can say it like this: not all of them are inside of the voting. That's it.
Yeah,
Once
but
a value is picked up already, they're going to send that value to the rest of the agents that did not participate in the voting. That's it. You can just understand it in that way.
okay.
So yeah, a learner could be, say in this slide, we have also S4 and S5, and they're not going to receive the prepare and promise, but they are going to receive the accepted message, which is the last one. So
Okay.
they're going to just write on disk the item, and they're going to act like well, just learners, where they just have like store the information.
Okay. And the other question that I have is, what happens if there are no majority?
If there is no majority, the system wouldn't work. Well, that's what I think, because Paxos, I mean, here is in bold, that it heavily depends on the acceptance of the majority of the system. So Paxos doesn't handle more failures than the majority of number of the cluster.
It's
Okay,
going
so
to another round is going to be set up. That's it. If not, the system is not going to work.
okay,
It's a consensus algorithm.
so each time a server gets a proposal, it's going to accept.
Can you repeat the question again?
Yeah, each time a server gets the proposal, the server is going to accept the proposal. So when you say that there are no acceptances, it's just when we have a communication failure.
Here you can check it out, or maybe in this one. So say in this part, S1 is the proposer and is sending some prepare messages. S3 here failed, but let's say also S2 fails. So S1 doesn't receive like any promise. He has his own promise because he's also sending the prepare message. However, majority isn't reached here. So S1 knows how many nodes there are in the system. So in this point, he knows that the majority isn't listening to me. They're not prepared to listen to me. So in this case, S1 cannot send the accept message. Because if he doesn't receive enough number of promises, this could mean that either a lot of the nodes fail, or that something else is going down in the cluster and another promises are being made and another promises are being made in the system. So in that case, well, just Paxos is structured that way. If a majority isn't reached, Paxos doesn't work. So
okay.
Is it clear?
Yeah.
Okay.
Further questions? No. Yes.
Oh, yeah, I have one. When you mentioned that the application is the one that decides the type of ID that will be used to recognize the agents, because in these examples we are seeing the ID 42.1 and then we have the timestamps. In this kind of selection for the timestamps at IDs, I mean, all we know that the timestamps will change through the time, or not through the time, through once we are receiving events. So how Paxos, or how I mean, this could be implementation defined in the application, right? Or on how the system does to recognize those IDs in case they are changing.
Yeah, Paxos doesn't describe how to choose an ID.
Okay.
So, as I said, it's the programmer's decision on what to
Okay.
choose.
So it will always be the application, the ones that defines this.
So
I
here,
have- yeah.
there are some pros and cons to the timestamp. The timestamp, we have the latest active server. However, we can reach the contention phase, which isn't quite good. But I mean, if we also choose this approach with where we have attached the ID of the server, we can prioritize some servers over others.
Okay, thank you.
Okay. Any other question?
It's not.
No more questions?
I have one, but I'm not sure how to explain it. When you were explaining about the learning agents, you mentioned that probably there could be two proposals at the same time, right?
Yes, there can be
in different groups of agents.
Can you repeat? I didn't listen.
Yeah, I think Juan mentioned that there could be two proposals at the same time. For example, one proposer proposes a value to a certain group of acceptors, right? And probably at the same time, there could be a different proposer proposing a different value, but a different set of acceptors. Probably
Yeah.
the same.
Yeah, actually, that is possible. There can be, if you're saying if there can be more than one proposal at the same time, yes, it is possible.
Yeah,
that is why
okay.
all of the servers evaluate that proposal. And as you said, there can be like clusters of proposers and acceptors, and the other ones can be learners. That is why it came in phase 2, all of them, they're going to receive that information. And if they're going to compare if actually it is the same proposal that they already received, because if there is a bigger one, they're going to just like reboot, not reboot, but they're going to reject the first one and they're going to accept the new one.
So yeah, I mean, if we have like 100 number of nodes and there are like, I don't know, 10 proposers. So they are all sending their prepare message and they receive some promises and stuff. But for one proposer to send the accept message, that proposer needs to get the majority of promises in a system. That's why majority is so important in this algorithm. So nothing is going to happen unless at least one of the proposer receives the majority of promises. So in this case, that majority of the nodes are already like locked on. They won't listen to anything else unless the proposer that they are promising to.
Okay, but yeah, I think it is clear now, because I thought that the proposer just sends the prepared message to a subset of the acceptors, but they send the prepared message to all the acceptors, right? And I don't know, probably some of those messages fail, and that's why the proposer doesn't get the response from them. But the proposer always sends the prepare to all the acceptors in the cluster, right? Not just to a subset, right?
Yes.
Okay.
Yeah, so the proposer want to be listened to. However, only the proposer with the higher ID is going to have like the final decision in this case.
Okay.
That's why also the ID plays an important role in this algorithm.
I think what is missing is that they say the servers that are not acceptors are learners. So they are going to send a message to all the servers, but just the acceptors are going to send a message, and
Yes.
learners are going to just to record the message. Is that true?
Yes.
Okay.
So any other questions?
No questions. Come on. Sorry. This paper puzzled like researchers for 10 years, as I mentioned, and you got it in like 30 minutes presentation.
Yeah, it's kind of hard to compile all of this in very little time. And also
Sure.
the paper is kind of complicated. It's not, even though Leslie wrote another article just to explain the previous article, it's still a bit hard to understand.
Yeah.
So if there is no more question, thank you guys. You can stop sharing. I'm going to share this screen like the way we do. Voting. So we want to achieve a consensus on on the grade. So about
Can you paste the link?
oh yeah, I got it here.
Thank you.
If I see the chat. Okay, so it's it's a little bit maybe sometimes unfair because like this is really a difficult paper. Honestly, it's like as they mentioned, as they talked, like Leslie Lamport was trying to. I mean, he came up with the paper on 1989. And he couldn't get it published till 1999. So for 10 years, no one accepting the paper, no journal accepting the paper because they couldn't just, how to say, understand it, but what he's talking about. So then he came up, I mean, he finally published it in 1999. Then after 2 years, he wrote another paper, the simplified version, the one that you're supposed to read. So it's difficult to basically understand. That's why Braft came around basically to let me show you this video, this short video. Just tell me if you're hearing the sound. Do you hear? No? Let me stop.
We can see it.
Yeah, the sound is important here. Let me share it with the screen too. Shared computer sound. Okay.
So finally, in case you're wondering, why did we pick the name Raft? Well, there's 3 reasons. First is that Raft stands for replicated and fault tolerant. Second, a raft is something you can build out of a collection of logs. And third, a raft is something you can use to get away from the island of Paxos. Thank you.
So that's basically Professor John Hautzer, okay, who is the co-author of basically raft paper with Diego. So they co-authored the raft paper, which is supposed to basically much simpler. That's why I just found it very funny the way he put it. Okay, why they came up with the raft name, so you can get away from the Texas island and basically to be able to understand it somehow and get away from what Lamport was trying to say. I'm confused. So if you allow me, I'm going to talk a little bit about it, then we're going to have a break, then we continue with the rest, okay? So just before I associate this is basically, as they mentioned, if you remember last time we talked about view stamp protocols proposed by Barbara Lisko. That was what we discussed last times in last classes. So basically by then, I mean, this Lamport, as they mentioned, they find out there is no mathematical proof to what they are doing. So he tried to come up with a better idea for consensus on top of their works for this Nancy Lynch and Barbara. So he came up with that paper. So and the rest of the story that we discussed. So as I mentioned, we can basically have two general approaches for consensus: symmetric or leaderless, okay, and asymmetric or leader-based. Paxos, the simple Paxos is a leaderless, okay. So all servers have equal roles. Client can contact any servers, but the multi-Paxos and the raft that we're going to see later is basically asymmetric or leader-based protocols. So basically, clients communicate directly with the leaders, and leaders does the rest. So it's make it much basically simplifies all the operation when we have a leader in the basically in our distributed systems when we are trying to achieve consensus in an asymmetric. So they mentioned basic Paxos, one or more server proposed values. Okay, system must agree on a single value as chosen, and only one value is ever chosen. And in multi-Paxos is basically combining several instances of basic Paxos to agree on series of values, because we don't want to agree on just one value. It's a series of the states. We're talking about that replicated state machines. So talking about basically the consensus, okay. We want to basically achieve this outcomes. Okay, we want all the processors that decide do so on the same value. Okay, that's what we want to do, right? So basically, what we don't want to happen is like a bad thing that should never happen. Okay, basically, bad thing that should never happen is the deciding on different values. Another thing is, the value that has been decided must have proposed by some process. Okay, the value cannot come from nowhere. And also, all non-faulty processes eventually should decide on the same value. Okay, this is a good thing that eventually should happen. If you remember these things, do you remember what characteristics of distributed system this was? Bad thing that should never happen, and good things that eventually should happen.
Is the liveness and the
completeness?
Completeness.
Basically liveness and
Safety.
Yeah, that safety was bad thing should never happen. Liveness was good things eventually should happen. So talking about the Paxos safety is like only single value is chosen. Only chosen value are learned by the processes, and only a proposed value can be chosen. So this is basically agreement. This is the validity. And for the liveness, some proposed value eventually is chosen if fewer than half of the proposed basically processes fail. And if a value is chosen, the process eventually should learn it. And these are basically the termination that I just talked last slide. So in general, when we're talking about consensus problem, we typically talking about basically coming up with basically deciding on single value, okay, or single value formation or formulation, okay. That's basically basic problem when we're talking about consensus problem. So they mentioned proposer, acceptors, learners. So here I was going to talk about just proposer and acceptors. Learners are basically acceptors that are not involved in the process of basically the consensus. Okay, maybe they fail, they come later and they learn what was happening in the system. Okay, so you can simplify it and just talk about proposers and acceptors. Learners are basically those systems that are not involved in the process for any possible reason, failing or being. So I'm going to here. I wanted to say, like for example, the strawman idea, or a simple dumb idea could be, okay, why don't we have one single acceptor? Okay, so sorry. So all the proposers propose that to the single acceptor, and then single acceptors choose one of these basically proposers. So the problem with this system would what if the acceptor crash, right? Then we're going to have single point of failure. So we could, for that reason, we could have basically a quorum of acceptors to deciding on the value. So then there are problem of the split votes if they achieve different votes, okay? There's a problems of conflicting choices. I'm not going to basically to go much detail, okay? But I really recommend you to go through my slide, just see them, okay? Because they are available. It's the same discussion, different presentation, okay? And I believe that the slides are basically when you see them, you can understand. So there are certain problems with using like this type of basically simplified solutions for consensus. So that's why basically in Paxos we had and about the basically proposal number that they were talking about. As they mentioned, we have a round number, okay, and we have a server ID to make it a unique basically proposal number. Because if you have a round number, all the basically the processes are working on the same round number, then you add server ID to make it a unique proposal numbers. And let me go to basically the same process that they discussed. You choose basically proposer, choose the proposal number, broadcast the prepares, acceptors hear that. If it's a bigger one, they send the prepare. Okay, then send accept, they respond by that, accept. So the problem that can happen, okay, maybe I try to make it a little bit more simplified here. Let's say we have 5 processes here, okay, 5 machines, S1 to S5. So S1 here, for example, propose a value, okay, with this proposal number, okay, we are in the round tree, it's proposed by S1, number 1. So it proposes, and basically computer tree system, they accept the proposal with this value X, okay, because S1 is proposing X. And on the other hand, S5 that is not hearing this, start proposing its own value, which is Y, okay. So S1 did it, and this is the time development, okay. So S1 did this proposal, got 3 accept, then this proposal from S5 got achieved to the S3, okay. But S3 before before that, S3 already accept value X. So S3 is not going to accept value Y. It's going to respond with the accept, and with this proposal number, the value that is already accept. as they mentioned, because the S3 already accepts this value, it's going to say, okay, I already basically accepted this particular value, and that value also will be propagated to the other computers. Okay, so it's if for example, that's why like S4 and S5 are going to hear this value X from S3 because S3 already committed to this. So there is another case that, for example, S1 already didn't have already the majority. Okay, so for example, prepare for this with the value X. S3 got this send accept. Okay, but let's say these are not yet arrived to S1, and meanwhile S5 is proposing its own Y value. Y value again. S3 going to hear another, let's say, proposal from S5 with the Y value, but because S3 already commit to this, okay, it's going to again accept the same value and propagate that answer to the same to the other systems, and at the end they're all going to achieve this, basically get to the agreement with this value. But another one can be like this type of scenario that so prepare or proposal with the S1 with the value X, and S5 is proposing value Y with PY. So PY is achieved to the S3. S3 didn't already send accept. Okay, the value is not accepted yet. So it's because it's not accepted when S3 get this basically proposal number which has a higher value, then this is going to be basically set for S3, and then when the accept basically message arrives to S3 is not going to accept this because it's already have the bigger proposal number. So S3 is going to reject this and stick with the basically proposal number 4.5 from S5, which has the value Y. So these are like a three scenario that can happen, okay, in the basic access. Is that clear? And then there is this basically problem that competing proposers can to get to a live lock. What it means, like there's a proposal from S1 here, there's a proposal from S5, there's no accept yet anyone. When the accept comes from S1, already S3 basically got a bigger number. So basically no one get the majority, S1 going to increase, okay? Let's say increase the round number, propose again. While it's doing that, then S3 get the accept from 3 for Y, but it's already have a bigger proposal number. So this can keep going on, and basically we call that live lock situation. So basically they don't get to the agreement at all. It can last long. So one solution for this is randomizing delay before restarting. So when basically before you allow them, for example, S3 to go for another proposal, you randomize them for all the computers. Okay, so randomizing that make it basically theoretically not necessarily happening, but practically they get to the agreement. Okay, and for, as you mentioned, multi-access use leaders, so we don't have this issue with leaders. So I'm not going to talk about multi-access, but there are some slides you can go through it. It's a little bit more complicated. You don't need to learn it if you don't want, but it's good to check it out. That's it from Paxos, but the more important one is the RAF, that basically you need to get it very well because you're going to implement it in the project tree. So let's have like 10 minutes break, coming back by 8 p.m. Okay.
Okay. Thank you.
Sorry. Can you see my screen?
Yes, I can see your screen.
Okay, we are group 7. We are going to talk about Raft algorithm. Well, the paper is defined as, well, it's named Raft in search of an understandable consensus algorithm. So, well, as a little introduction, resuming a little of definitions, we are defining here what is a consensus. Well, consensus is the task of getting all members in a group to agree on some specific value based on the votes of each member. So we can think of a consensus like when a group of friends are going to decide where are they going to eat together. So they organize something like a votation, and the majority of it is where they are going to go. Or more related association is like an ideal democracy, where members of a group decide who is going to be their leader, new leaders and such. So here in the context of distributed systems, this type of consensus algorithms are commonly used to handle state machines replication. So we are defining state machine replications. That is a method to implement fault tolerant service, replicating servers and coordinating them, coordinating the replicas to achieve the fault tolerant service. Well, in this context, the state machines use replicated logs. So here we see an illustration of it. Clients make requests to a server. The first step is using the consensus module, first decide a leader, but also the consensus module in Raft is used to replicate the log. And well, once the majority of it agrees, the members of the group commit their logs and update their state machine. That is like its current values that they have now. And only once the majority committed the state machine, a response is sent to the client. So this is the flow of how the consensus and log is replicated. Here we are defining the replicated log. That is the copy of the same log in all the members of the groups, all the members of the system. Sorry. In state machines, the log, each entry contains a command, an operation, or something to perform in the machine. And when they execute the log, one rule of it is to execute it in an identical order to always produce the same result. For this, also the commands that are included in the log must be deterministic. It means that no matter what, the commands will always produce individual same results. So that way the log will always produce a final result identical in each server. And well, now we have in the context, Raft is a consensus algorithm for managing a replicated log. Was designed as an alternative to Paxos, and it was meant to be more understandable. Yeah, here is also why it's named like that. It stands for reliable, replicated, redundant, and fault tolerant. It was released in 2014. So, yeah, well, the objective of Raft was to actually, well, it is defined as a more understandable consensus related with Paxos. In the paper, it's all the time comparing how Raft is doing things different as Paxos. Well, here we say that it's way more recent than Paxos. Yeah, the motivation to migrate from Paxos to Raft is that Paxos is very difficult to understand. And even more than that is when programmers try to implement it, there are no easy way to abstract the definition to programming languages. So now an overview of how Raft works. Raft implements consensus. The first step of the Raft is elect a distinguished leader. And then when the leader is elected, he is responsible to manage the replicated log. He and only he, all of the rest of the members are not going to to manage the replicated log. The leader is the only one that accepts requests from clients, and he is the one that replicates them on the servers. And he will know when the other servers are safe to apply the same log. So, well, this is about how the leader is going to be managing all the process. And yeah, as an important key, at any given time, each server is going to be in one of these three states. He can be the leader, or he can be a follower, or he can be a candidate. So there are also three states as in Paxos, but they are different and they do different functions. See, and a rule of Raft is that there is always going to be only one leader, and the rest are going to be followers. Yeah. So when the system starts with Raft, all of the members start.
Marco, sorry, I am available now.
Great. Well, I just talked about the Raft overview, and I was starting with leader election.
Yep. So for leader elections, a typical configuration of servers are 3, 5, and 7 nodes. More than that, it's very uncommon. We are focusing on a system made of 5 nodes. And Raft uses a heartbeat communication mechanism to trigger a leader election. When the servers start up, they begin as followers, all of them. And the second phase, if there is a election timeout, this election timeout is randomized between 150 and 300. And if we get an election timeout, then to begin an election, the follower increments its current term. If, for example, all start in 1, the candidate pass to another term that is, for example, 2, and transitions to a candidate state. Now, that node, the candidate reply for a vote for all the other servers, and also the candidate vote for himself. So 3 things can happen. That candidate win an election. B, another server wins because could be another candidate at the same moment. And C, it could be no winners. We will see that that point in a fewer detail. Yep. And once the candidate wins, becomes in leaders, and again use a heartbeat to make the other servers awake and alert for the leader to avoid the election timeout. So we will see a graphical explanation of this in a fewer examples.
Yeah, well, only to complete the process of Raft. Once the leader has been elected, now he is responsible to manage the log replication. So he starts receiving client requests. Each client request has commands, we tried before, and they have to be executed in the state machines. Here we have just a simple illustration of how we can have 5 servers in the system, and each server has its own log. And well, this scenario is the ideal scenario of a replicated log, in which all of the commands were replicated in all of the servers with no troubles. And here the 2 is what David mentioned. The number of the term is like the number of the leader that was, no, the number of the moment. It's like a number of time. I mean, in time 2, all of these commands were committed. But then this number 3 means that another server became the leader, and he started to handle the replicated log. Well, we will see how this works in a couple of more slides. Yeah, well, he's describing a little more how the leader appends, when he receives a request, he appends the command to its own log, and then requests the other servers to replicate the entry using RPCs, append entries is described on paper. The leader requests the append entries to the other servers. And when the other servers have safely replicated, then the leader can apply or commit that command to the machine and return the response to the client. This is another, well, a more real replication of log, in which, well, at index 1, 2, and 3, everything was fine. But we can see at the moment 4, there was inconsistencies. Here we can see that server F became leader with the next term, but well, he could not replicate this command to the other servers. We don't know why. It might be because some crashes of servers or not messages were received. So if he didn't receive the majority of commits from the other servers, so the other servers are not going to include it in their log. And at the same moment as he couldn't replicate the command, another server, as they didn't receive the response from their leader, became itself a leader and started replicating the logs. Here we can see that we don't know who was the leader here, but he could replicate the log in the majority of servers. So that's why the log starting to be committed with term 4 instead of term 2. And so on. In some scenarios like this happen of leader crashing and new leaders becoming and handling the replicated log. A little ahead, we will see the construction of this in a real scenario.
Okay, for safety, those properties guarantees that each of these properties is true all the time. So election safety, we at most one leader can be elected at given time. There is no 2 leaders at the same term. Leader append only, leader never overrides or deletes entries in the log. Only if that entries are committed. If they are not committed, it could be an override or delete. For log matching, if 2 logs contain an entry with the same index and the term, they are identical. So we have a log matching if we have a log in the same index and the same term. And leader completeness, if a log entry is committed in a given term, then that entry will be presented in the logs of the leaders of number 9. So a committed entry, it's always in all the logs for subsequent leaders. State machine safety, if a server has applied a log entry at a given index at its state machine, no other server will ever apply a different log of entry at the same index. So we don't care if we have a new leader, it must be respect of the index in the log. So no, it could be an override or delete of that at that index. So in the next one, this is a rule for election restriction. The voting process prevent a candidate from winning an election only if its log contains all committed entries. So a leader that may be disconnected in some phase, if he wants to become a leader again, it could be a little late for the new entries. So he need to back up and up to date that entries. And another rule, if the logs entries have different ends, the log with the later term, it's more up to date. So we don't care of the length of the log. We are focusing on the term that it's the bigger one. So that, for example, that first one is true because we have a term of 4. Committed entries from previous terms. That's another rule. Raft never commits log entries from previous term by counting replicas. So, for example, in S1, this bold box is the leader. So in the index 1, we have replicated all commit data, but in the 2 phase, we don't have the majority of all the entries. So we have only 2 of 5 entries in all the servers. So in the V case, the S1 was disconnected or failed. So S5 took the leadership, and it tries to replicate the 3 entry in all the other 4 servers, but unfortunately was disconnected, and 1 becomes a leader again and tries to write a new entry. But this is the tricky part. If we have an entry that was not committed, the D case could be available because we don't have the majority. So we need to pass the leadership for another S5 because we are supposing that S1 fail again. So D tries to replicate all the entry in all the 4 nodes. But what happens if S3, that entry was committed and the E was possible? So we start to replicate it, all the entries in all the 5 nodes because we have a majority. So if there is a majority in the log entries, the next leader needs to continue replicating that entries. If there is no majority in all the servers, the new leader could erase or overwrite that entries that are not committed. The next.
Okay. So here at this point, the creators of RAF have this GitHub page in which they have a way to simulate how the RAF algorithm works. I don't know if you want to take the screen. Maybe.
Yes, can you please stop the, yeah. In this one, I'm going to show you how an election is made, a successful election. So we have all the terms in one. So a little bit slowly. So the steps are, all the servers start up begin as followers. So all of these as followers, and this bar is the timeout. So we can see all the bars are different sizes because it's a randomized election timeout. In the second phase, we have the S2 reach a timeout, so it becomes a candidate and request votes for the all the followers, and they send a positive vote, so you can become a leader. We have a five cluster, so we have a majority of 3. So because S2 votes for itself, so in that moment, S2 knows that he is the leader, so sends the acknowledgement for all the others servers and begins the term. So this is the leader now. If nothing fails, it's always be the turn to the leader, the S2. So this is a successful case that to make the things a little bit easier, we have 3 nodes, but in this case, a little, I have to reset. We have 3 nodes. So what happens if I have a reach timeout and a timeout at the same time? So we have 2 candidates, and they are going to request the votes for all the followers. So one candidate votes only one time at a given term. So S1 requests a vote for S2 and S3. S3 votes positive, you have my vote, but S2 votes negative because I am the candidate. So S3 votes negative to S2 because we already say that S1 is it's my leader. So at that time we have no winner. So what is going to happen next? It's we need to wait the timeout again, and we have another voting process because they are giving the same timeout at the same time. So this is the more complex way. So at that moment, only at that moment, we have a new leader. So this is one disadvantages of the RAP, because we are losing time because we don't have a leader, and because it's lost time. So for other cases, in that example, we are making entries for all for this term two. And it's all committed, it's all okay. But at the given time, S3 was disconnected for unknown reasons and stops to append entries in its log. So what happened? S3 wants to become a leader, but all the nodes votes negative because, okay, you don't have all the committed entries from, or the same entries as we have. So you can't become the leader because you are late. So we start another timeout, and eventually we have an S2. We have 3 candidates at the same time, but is to become the leader because all the nodes vote for him. At that comment, it's all okay. And at that moment, is 3 was recovery, so all the entries are committed. I have more examples, but there are the restrictions. This is the previous one. We have a two candidates at the same time, and this one. This is what happened if we have an entries that are not committed and a new leader comes up. So is for S4 and S5 was there is an entry, but they are not committed. So the new leader is 3, term 3. The new leader is 2. So we have those entries, but we could also rewrite or delete those not committed entries, and all the log is back okay. So that's for election leader, and Marco will show you your screen.
Okay, just taking some points. We can see, well, David mentioned the requesting of votes done and a leader gets elected. What we see here that the leader keeps all the time sending to all the nodes. Those are not requests. Those are what we name heartbeats. Those heartbeats include some information to the other nodes, like if they are late in their log, these heartbeats have the information to know that some server is late, and then the leader will send the logs that he doesn't have. And other things, like as you can see, the servers are trying to become leaders. Their timeouts are reducing, but every time they receive a heartbeat from the leader, well, the timeout increases again. So this prevents another server from trying to be elected leader when there is actually one leader working. Well, then only the leader can accept requests from clients. So here we see that we append a request from to the leader, and okay, a little slower. We append a request, and the first thing that he does is, okay, he received the request, he adds that entry to its own log, but you can see the entry is dashed line, is because that entry is not committed yet. To be committed, it requires the acceptance of the majority of servers. So what we will try to do, he will try to do, is send these append entries RPC to the rest of the system. Here we see this request to all of the nodes. When they receive that message, they add that entry to their log. But as we said before, this dashed is dash line because also that entry is not committed yet. A log entry is committed in two phases. One is the communication of the log entry, and a second phase is the actual commitment to the log. So the first phase at this point has been reached. All of the servers receive the command, and they respond to the leader. Okay, we added to our own logs. The leader receives that, and at that moment, as he received the majority of acceptances, S2 now actually committed this entry. You can see now the full line, but the rest of the servers are still in dash line. That means that they haven't committed that entry yet. To be committed, they need that second phase in which the leader say, okay, now you have to commit that entry. And this is what happened next. The leader sent this heartbeat. Now the heartbeat also includes information about the log entries that they need to confirm. So the heartbeat is an important mechanism of Raft. The heartbeat includes all the time different information depending on the necessities of each server. So here, let's focus on S1. He is about to receive his heartbeat, and in the moment he receives it, he will commit that entry. You can see he already committed and responded, okay, I committed, and the same thing happens with all the servers. So this is how the replication of the logs happen. We can simulate any case that you consider important here, but in this case, two nodes fail, and we can add another request to the leader. And what happens? Well, as he receives the majority of acceptances, well, the commitment of any new request will complete successfully. But what happens if we stop another server? So there's now only two servers, the leader and a follower. And if we add a request, this will always stay in uncommitted state because he's not receiving a majority of acceptances. So at this point, if the leader crashes, and let's say other servers resume, and let's say that one of the new servers time out, and he will try to become leader. So he will request the votes, and well, based on rules, the other nodes will vote. We can see different voting. From S5, he receives a positive vote because the log that S4 has is the same as S5. So he says, okay, we are in the same log. You have my vote. But we can see S1 and S3 voted negative because they have more log entries than the candidate, so they are voting negative. So he will not be able to become leader in this scenario. He needs the majority all the time to become leader. but if he doesn't have an up-to-date log, he cannot become the leader ever. So what happened here? Another server will time out, and eventually a leader that actually has the up-to-date log will win. We can try. Okay. Well, I think I missed this. But well, what happened is that as one that actually had the log up to date win the vote of a majority. And in the subsequent heartbeats, he sent the pending entries to the nodes that were late. So eventually, all of the nodes that are in the system will complete their log. And yeah, this is mainly how it works. I don't know if someone wants to ask for a scenario for this. If not, we can go back to the presentation to mention some important keys of this. Okay. Here we are describing what happened when a follower or a candidate crashes. In the case of a follower crashes, well, as we saw in simulation, when they are down, any request of vote that they receive, I say, will fail. So, crashed servers cannot obviously respond votes. So the leader will be retrying and to see if he gets the majority, but if he doesn't get it, another node will try to get it. When the server crashes, oh, this is a more complex case. As we said, there are two phases when replicating an entry of the log. One is when it sends, and another when it commits it. But what happens if the server crashes when it actually completed the command but was not able to respond? When he restarts, he will be receiving the same log because as he was not committed, the leader will be sending him the log that he is missing, and but eventually he will respond the commit of the log and he will get up to date. This is what we mentioned in the beginning, that the commands that are introduced in the log are that I said deterministic, he said idempotent. What it says is that once a node once a server receives an entry and includes it to its log, in the scenario he crashes and goes back again and he receives the same log entry request, he will ignore it because he already had it, so he will not execute it again. What he's going to do is only respond the commit of the log command, but he is not executing twice or many times the same command. So this is the possible scenarios when a follower crashes. So okay, move on.
This is a very logical matter, because the broadcast time is the time to the leader to reach the follower. So the election time must be bigger, because we don't want election timeouts all the time. And the MTBF is the mean time between failure, is how long a new or repaired system will be run before failing. So that could be months. So this is this is an example. The broadcast time is 75 milliseconds. The election timeout could be randomized, obviously, but 200, and the MTBF could be days, 45 days, for example.
Well, here it's an important scenario that can happen. In previous slides, we saw a configuration of 5 servers at the beginning, and it maintained all the time. But there is the possibility that the administrators can want to, I don't know, replace some servers or remove or add others or something like that, changing the configuration of the system. And one possibility to do this is to shut down the whole system, but that will, well, produce inavailability of the system for the while that they change to the new configuration. So the way the draft manages these configuration changes, yeah, well, you see that occasionally is needed to change the configuration. What draft does is a transitional configuration that is called joint consensus. And once that joint consensus is committed, now we can migrate to the new configuration. We can see it here. There are three phases in time. In the first part, the CO, the configuration, all the initial configuration is working, but at some point, a new configuration is requested. We can see it here in the see all new. And what happens is that the leader begins to starts to saying to the members, hey, there is a new configuration. We are going to migrate to this configuration. And only once the majority accepted, uh, the the intermediate configuration is applied. In this configuration are included the nodes of the first configuration and the nodes of the new configuration in a same one. They are living together, and each new entry that comes at this moment will be replicated in both old configuration and new configuration. And then once this transitional configuration is stable, now the new migration to the final new configuration happens in the same way. The leader starts saying, hey, we are going to migrate to this actual new configuration. And only when the majority agreed, they are now in the new configuration. So doing this, the system does not lose the availability. He keeps receiving requests and replicating them safely in both configurations to not lose any command entry. We see well, the is here. Also, yeah, in the moment of the transitional configuration, it is necessary that both groups that are living together, both majorities vote for the entry. If only the majority of the first configuration votes positive, it is not possible to commit that entry. It needs that the majority from both old and new configurations vote for that request to actually commit the things that happen here. That way, it's ensured that not any log entry will be lost. Okay.
For the log compactation, as the log files grows longer, it occupies more space and takes more time to reply to other servers. So RAF uses a snapshotting. So it's a simple approach to the compactation. Each server takes a snapshot independently, covering just the committed entries in the log. So at that point, consensus has already been reached when snapshotting. So we are only covering the committed entries. Raft also includes a small amount of metadata in the snapshot, uh, like the term, included index term, and the state machine at that index, for example. The leader uses RPC called install snapshot to send snapshots to followers that that are too far behind. And when to do, it's one simple strategy. It's to take a snapshot when the log reaches fixed size in bytes. So it's defined by us.
Well, here are a couple of things related with the client interaction. When a client makes a request, well, the client does not know who is the leader. He will only make a request, and that request can end up in a node that is not the leader. So that server rejects the client request, but what he can do is to supply information about the more recent leader that he knows. So the client will send the request again to the leader now. So there is only one extra step from the client to reach the real leader. And well, this is all again the case when a client, let's say, clicks 5 times very fast the request. So 5 requests are sent, but well, the leader in this scenario, the leader crashes after he commits the command, but he didn't respond the client. So the client is trying and trying again. And this means adding a lot of the same command requests. But this is, as we said before, will not end up executing a lot of times the same request because each command has a unique serial number assigned. So when nodes receive commands with the same serial number, he will know that it has already been executed and the servers will respond the answer, but they will not re-execute the request. So that is how it's handled multiple requests for the same command.
For the evaluation or performance, RAF's performance is similar to other consensus algorithms such as Paxos, but the main topic is the evaluation, the election timeout. So, for example, in the top graph, there is a small amount of randomization in the election timeout to avoid the time to reach a new leader. So just adding a few milliseconds in the randomization, we can, in the point of the 150, all the nodes has 150 milliseconds in the randomization. So it could be as long as 10 seconds to reach a new leader. But just adding a few milliseconds in randomization, it drops like a lot. Only took a few milliseconds to reach a new leader. And for the bottom graph shows that downtime can be reduced by reducing the election timeout. So we are using, for example, 150 to 300, but reducing that time, we can reach a new leader in only 35 milliseconds. The longest trial, it says, took 150 milliseconds. So just adding a little bit of randomization in the election timeouts, it could be way more increasing performance.
Well, just to finish, the creators in the same page that we said before, they include all of the many implementation of the algorithms in different languages. So we can see there are well, a lot, and there are a lot more in their page. But well, we can see Rust is widely used in several languages. Yeah, I think that's it. We have now questions.
Anyone has questions?
Yes. All the RPCs that you mentioned, the append entries, install snapshots, those RPCs are part of Raft, or some of them are also part of the Heartbeat process that is used for the leader election.
Yeah, all of them are part of Raft. Here in the paper, let me just, there is a collection of the possible requests. You can see the append entries, the votation requests. Well, mainly those.
Okay.
These are the rules that the nodes have to vote positive or negative to the leader election or to the commitment of logs. But yeah, the answer is that those RPCs are part of the definition of it.
Okay, and for the Heartbeat, is there are there any specific RPCs? I mean, or for the Heartbeat in the leader election? Because I wonder that the way these log entries are provided to all the other nodes, it's through RPCs. I think.
I think it's append entries.
Okay.
Empty for Heartbeat. So okay. We can, in the entries part, log entries to a store. Empty for Heartbeat. May send more than one for efficiency.
Thank you.
Any other questions? Was it more clear, Raft and Paxos? Okay, so if there is no question, thank you guys for great presentation. Really, you covered everything. I'm not going to talk at all. Okay, you covered everything. So let me share with you my screen. It's the same previous link that I sent you in the chat. Last link. Just one thing they were talking about, I just mentioned, they were saying a lot of time, like for example, server fails and comebacks, and basically you can continue from that stage, okay? Because you remember the basically servers, or like you're saying processes, they write the logs in a hard disk, okay? So they can survive the crashes. That's why basically they were mentioned a few times that, so just remember logs is writing on a hard disk and they can survive crashes. And another thing to remember is the truth is in the log of the leader. I mean, at the end, when you choose the leader, basically the truth is the log of the leader in the raft. And yeah, I mean, they cover really everything. Anyway, my slides are available. Maybe some of them just is more graphical, okay, but exactly whatever they mentioned. The paper also is really readable and easy to understand. So there shouldn't be any problem understanding it. But if you had any problem getting it, this paper, I mean, this is basically the author himself talking about the paper. Okay, so it's
Becomes leader and takes over the cluster.
very much like,
Okay, that's one.
I mean, if you had any hardship understanding it, just watch this. And for the Paxos, if you have any hardship understanding it, watch the link that they share in their last slide, the first link. It's like 30 minutes video. The guy is like talking about the Paxos using pizza, burger choice, okay? And it's very easy to understand. I mean, he explained it very nicely to simplify it very nicely, so it's understandable. So, okay, before we finish the session, there was a question about what I'm expecting about the assignment 2 about the summaries. So I noticed there were a lot of hardship on coming up with the papers, okay, but finally we got it. Okay, so almost all the papers are fine. There were just 2 papers that they are themselves, they are survey papers. So I have a little bit doubt how you can summarize a survey paper, which is a summary of a lot of other papers. So it's like, if it's not impractical, it's really difficult, okay? Because a survey paper or a review paper itself is a summary of a lot of review papers. So I have just doubt about these 2 papers. The rest are really interesting, all of them. As I mentioned last time, I think it's the last change. So what I expect you to do is basically read the papers. Maybe sometimes you need to read them two times or 3 times to understand exactly what you're doing. If you read one time, you didn't get it, it's not your problem. It's a normal process with a paper reading, okay? Because as the author, when we write it, we have everything in our mind, so we think it's super clear for everyone to understand. But for the reader, usually they need to go through it 2-3 times to understand exactly what authors are talking about. And I want you to write it in a way that when I read it, because at the end I'm going to read all this basically summaries that you're writing. So I want, when I read it, understand exactly what the authors are talking about and what they did. Of course, not with the complete detail of the paper, because you cannot include all the details. And then you're going to basically, most probably you're going, for example, the paper like consists of abstract, then there's an introduction talking about the background. Then they have the methodology, what they did exactly with a very detailed methodology, then what the result they got, the studies, and then they conclude. So most probably you're going to basically talk a little bit, at least a paragraph about the background of the study, okay, about background of the topic that you chose, okay, maybe 10 lines like that. Then what the paper is doing, what those authors are doing, not again including all details, because you shouldn't go beyond one page. Then most probably you're going to talk about another like paragraph about what the result they achieve, and if basically you include your own understanding of the papers. Like if they miss something to consider, or if they fail to consider a point, or if they were great in something, they have to realize certain disadvantages of the study. That, for example, if you want to do the research on that topic, you could cover, okay, they didn't talk about this or they didn't consider this. Maybe that can be something for the future. Okay, that can be another study that one other researchers come and concentrate on that. So most probably you're not going to talk about the literature review there, okay, in your summary, just the background of the study, the background of the topics briefly. Then most probably not going to include their methodology in detail, just like a very summary of it, okay, what they did. And then what the result they got, and maybe, again, but I'm thinking what result they got is, it can be like 2-3 lines, okay, because you're not going to put the result and discussing what the result they're putting, if there is a result. And then putting your final like touch, like your final output understanding, talking about advantages, maybe disadvantages of their approach, and so on. What's lacking, what they did right, what they didn't get right. It's clear? So make sure you don't go beyond one page. It's maybe fine, you include one image, preferably not, don't include any image, okay? Just purely text. And yeah, that's it. There is no, I mean, as I mentioned, there is no like word count, there is no line count, but just make sure it's more than half a page. It's not just like 3-4 lines. They did a great job, and put the title that they did this and they did a good job. Okay, not like that, but so just make sure it doesn't go beyond one page maximum. And for evaluation, if that's your, I'm going to put the peer review just for the sake of you checking other people's works, but the grading will be just totally on me, okay? But if for the peer review, if you got the paper to review, I mean, other people's summary, read it and put your comments. I mean, it would be great sharing your insight also about others people's summary, but the grading would come directly from me, okay? Any questions, doubt? So again, another thing is questions? Okay, another thing is quiz 2 is ready for you to take. Go to quizzes. So you have almost 6 days to take the quiz, okay? Quiz 2. From 3 till Tuesday next week.
That's quiz 1.
No, sorry. No, quiz. Miss, wrong click. So yeah, this one. Okay.
It's the same, right?
Ah, what the? I'm clicking on quiz 2. Ah, it's actually switched them. Okay. Yeah. So this is the one. So deadline is basically October 20 is the deadline. Okay.
The quiz, the description said by you to RAF, but then said RAF and Paxos are not included.
I mean, by your raft, so raft and Pax. That's why I put this to make sure what I'm talking about. Raft and Pax is not included. So till all the topics we discussed before this week.
Okay.
Okay. All good?
Can you repeat?
Yep.
I mean, is it included or not?
No, it's not included.
Oh, okay.
Access and raft are not included.
Are they going to be included in the next?
Yeah,
Seminar?
of course. Yeah. That's it. That's the bad news.
And the assignment is for this Friday, right?
Assignment is for,
Yeah, it is.
yeah, for October 16, midnight.
Okay.
Is it good, or anyone has problem with the deadline, or
It's good for me. I don't know the other ones.
anyone has any complaint about the deadline?
No.
Okay,
No complaint.
perfect. So
Maddie, quick
yeah.
question. And
ahead.
about the quiz is from Bayou to Raft, right? Because I read that Raft and Pexes are not included on
Yeah,
Okay.
are not. Maybe
No.
it's coming.
Yeah, but if you see your
Yeah, that's why I said it. That's why I put that to make it clear, because
I'm confused.
because I knew it's confusing. That's why I put
It's my poor bad.
I put draft and taxes are not included to make sure. This is the like final truth, because it's the highest basically.
Okay.
Okay. But this is the last basically entry. Okay, so it has the truth. Draft and taxes are not included.
Okay.
That's what I remember last time I checked question. They are not included, and they are not. So remember, next week we have a project presentation, project 2 presentation. So see you next week.
Okay.
Okay, guys.
See you.
Take